Okay, hi everybody. We're going to be going over the Hardy-Weinberg questions that I assigned for homework back on the 13th of March. A couple of things to remember when doing problems like this is we always want to do things in a certain order, and that is, first of all, we want to find q squared for each question first. The second thing is we want to find Q, then we want to find P, and then from there we can figure out whatever the question is asking us. And generally, it wants us to find 2PQ or P squared as the final step. The whole point of this is an exercise in tracking genes and where are the genes actually their frequencies, how are they changing over time. And in general, if we're going to take our alleles P and Q, which represent the dominant allele and the recessive allele, when we add the number of dominant alleles, and an example of a dominant allele would be big A, and we add that to the number of recessive alleles, little a, it should equal 100% of all of the genes in the population. If we extend this to genotypes, we have to remember that the genotype P squared, which is big A in this case, because it's A times A, big A times big A, added to the number of heterozygotes in the population, which is 2PQ, that's 2 hybrids, added to Q squared, which is 2 recessive individuals, little a, should equal, again, 1 or 100% of the population. We use 1 because each one of these values should be a decimal, because we're talking about frequency. The reason why this is in a 1 to 2 to 1 ratio of big A to big A little a to little a is because we're assuming that the initial population is heterozygous. And if we cross two heterozygous individuals in our population, we get a 1 to 2 to 1 ratio of big A to big A little a's to little a's. So that's the premise of doing each one of these questions. So if we go back to the first question and we examine what it's asking us, the way we set this up is it says there's 1,000 people in a human population, 840 of them are tongue rollers, and the problem with being a tongue roller is there's two ways to be a tongue roller. You can be dominant, completely homozygous, you can be dominant heterozygous. We can't start with either of these values because these values have two variables, especially in the heterozygote population. So since there's two ways to be dominant, we cannot start with 840. We have to start with 160 individuals who are the recessives, and here are the recessive individuals, little t. And so what we have to do first is a step before we can actually do step 1. We have to take 160 and divide it by 1,000, and we get our frequency of 0.16. This represents our q squared because they're telling us right here little t is 160 out of 1,000. Now that I have q squared, I can solve for q. The way we solve for q is we have to take the square root of q squared. That's going to give us q. The square root of 0.16 is going to be 0.4. That represents little a, or in this case little t. That's q. That's our recessive gene. This number is this right here, this q. If we take this number and we insert it into this equation, P plus Q equals 1, we do this. P plus 0.4 equals 1. Now I solve for P by subtracting 0.4 from each side. P equals 1 minus 0.4. P equals 0.6. That means 60% of the population is dominant big T. They're asking in the question, what is the frequency of the dominant allele, big T, in the population? This is our answer, 0.6. Okay, moving on to question number 2. We're going to solve it in the same way that we solved question number 1. In a population at genetic equilibrium, and genetic equilibrium refers to this particular equation, that the number of homozygous dominant plus heterozygous dominant plus homozygous recessive individuals in the population should equal 100% of the population. That's the definition of genetic equilibrium. So this term means that we have satisfied this equation, and that should be true if we're following the rules of the Hardy-Weinberg equilibrium. They're telling us the frequency of big A is 0.5. So they're telling us P equals 0.5. Well, if we know that P is 0.5, then we can now figure out what Q is based on that to help us figure this out. It's 0.5. We get that because P plus Q equals 1. And so 0.5 plus 0.5 should equal 100% of all of the genes. Remember, this represents the big A, this represents the little a. What is the frequency of the homozygous dominant genotype, big A, big A? So if they're asking for what is big A, they're asking for what is P squared. That is 0.5 times 0.5. The answer to that is 0.25, or 25% of the population is homozygous dominant. What is the frequency of the heterozygous genotype, big A, little a? Well, big A, little a, if you remember, is 2PQ. We get that information from right here. This is heterozygous. There are 2 of them in our Punnett square. So to figure that out, it's 2 times 0.5 times 0.5. So that equals 0.5. So this is our answer for P squared. This is our answer for 2PQ, the heterozygous. All right, question number 3, following the same rules that we've been doing now. They're starting us off with 96% of garden peas in a population is tall, and tall is dominant. So if you notice, there's 2 ways to be tall. We cannot start here. They're giving us P squared plus 2PQ. So we can't start with this because there's too many variables there. We have to start with Q squared, which they're not necessarily giving us, at least not obviously. So let's start with this 96%, and if I take 100% and I subtract 96% from that, I get 4%. That's the percentage of recessives in the population. This is my Q squared. If that's my Q squared, well, that should be 0.04. So if I take the square root of Q squared, the square root of Q squared should equal Q. And so by taking that, square root of 0.04 should give me 0.2. If you don't believe me, check your calculators. You should have a calculator when you're doing these questions. So this is my Q. They're not asking for Q, they're asking for dominant, and dominant is P, just the allele. So if that's Q, and I know that P plus Q equals 1, and P plus 0.2 equals 1, then P has to equal 0.8, or 80% of the population. Okay, so if you're following along at home with me, now we're going to do question number 4. Question number 4 is actually, well, it should be much easier now that we've been doing these first 3. They're giving us 16% of a population at genetic equilibrium is recessive. Well, that's nice because they're giving us Q squared. So if Q squared is 16%, well, that's 0.16 because we have to convert that into a decimal. It's frequency. Then I take the square root of Q squared. That's going to give me Q. That means the square root of 0.16 should be 0.4, or 40% of the population has a recessive allele. They want to know, what's the frequency of the recessive allele in the population? Oh, well, that's easy. We just figured it out. It's 0.4. Second half of the question, what's the frequency of the dominant allele? Well, P plus Q equals 1. P plus 0.4 equals 1. Solve for P. P equals 0.6. 60% of the population has a dominant. Okay, moving on to the next question. It's asking something different. It's giving us the number of moths in a population is 1,600. 64 of the 1,600 are showing the recessive phenotype. So what they're telling us is 64 of these moths out of 1,600 are Q squared. How do we know? Because they're telling us right here, little q, and they're giving us little b, but it's the same thing. It's Q squared. Then 1,536 show the dominant phenotypes. Well, we can't do anything with that. Assuming that this is a random sample of the wild population, here's the difference. Is the population at genetic equilibrium? If this is the question, that means what they want us to do is they want to plug our values into the Hardy-Weinberg equilibrium equation. P squared plus 2pq plus q squared equals 1. They want to know, does it equal 1? That's the question. So what they want us to do is solve for p squared. They want us to solve for 2pq, and they want us to solve for q squared, and they want to know, does it equal 1? That's what they're looking for. Okay, so the first thing we do is we do 6,400 divided by 16. And so if you do 64 divided by 1,600, you're going to get 0.04. And so 0.04 is our frequency. That's 4% of the population. So that already sets us up right here. This is 0.04. Oops, 0.04. There we go. Okay, so we've already solved for that. Now, let's solve for p squared. Off to the side, I'm going to take my q squared. I'm going to put it over here, 0.04. And I'm going to take the square root of q squared, and that's going to give me 0.2. So that's my q. Now that I know my q, I can solve for p. P plus q equals 1. P plus 0.2 equals 1. That means p equals 0.8. 80% of the population has a dominant allele. 20% of the population has a recessive allele. Okay. If I take this number and square it, if I do p squared, that's 0.8 times 0.8. Well, that should be 0.64, right? So let me take my 0.64 and plug it in over here. I have 0.64 plus whatever this is. I don't know what that is. I have to solve that. How do I solve that? I just plug in this number and this number. 0.2 times 0.8 times 2. So 2 times 0.8 times 0.2 should be Well, 8 times 2 is 16. 16 times 2 is 32. And so what we're doing is we're putting a decimal place in front of that. That should be 0.32. So now we take our calculator, and with our calculator, I take 0.64 plus 0.32 plus 0.04, and I equal 96.04. I did that wrong. 0.64 plus 0.32 plus 0.04 equals 1. There we go. Yes, it's in Hardy-Weinberg equilibrium. All right, question number 6. Here's the problem with question number 6. They're giving us a population where 60% of the population is homozygous dominant. No one is heterozygotes. And 40% of the population is homozygous recessive. They're giving us our allele frequencies, and they're telling us that this population should be at genetic equilibrium. And the question is it? Why or why not? Well, there's a couple of ways to answer this, and it really depends on how you look at this. If this population of big A's, of which there are 60% of them, are isolated from this population of little a's, of which there are 40% of them, then it's not a population, it's two populations. And so we can't have this happen. Because if this were the case, yeah, you can have an entire population of big A's, but then that would be 100% of the population. That population. If 40% of the population were little a's, they can only mate with each other, and yeah, they'd all be little a's, and you'd get no heterozygotes because we have a barrier. We have some geographic or reproductive barrier here, but they're not saying that. And so the problem that we have is that if we remove this barrier, and we allow them to mate with each other, they're going to produce big A, little a offspring. But they're telling us there are none. And so what that means is something is selecting against big A, little a's. In other words, the heterozygotes are selected against. And one of the rules of Hardy-Weinberg is that there is no natural selection. So, is it at genetic equilibrium? No, it's not. Why is it not? Because you're not allowed to have natural selection, and that's what's going on. Okay, next question, last question, number 7. 30% of the population of Americans are non-tasters for a chemical called PTC. That means 30% of Americans cannot taste this chemical, which is a bitter tasting chemical. 70% of the population can taste it, and they are either of these two dominant conditions. Assuming the population is at genetic equilibrium, estimate the frequency of the alleles, which is then asking for Q and P. That's what they're asking for. What are these numbers? Okay, so they're telling me 30% of the population is Q squared. And so if I put that into a decimal form, that's 0.3. If I take the square root of Q squared, I get Q. And so if I take the square root of 0.3, I get Q to equal 0.55. That's Q. If I take that number and I put it into this equation, then P plus 0.55 should equal 1. Solving for P, I get 0.45, or 45% of the population possesses the dominant allele. I hope this was helpful for you. If you have more questions, if you'd like to do more of these Hardy-Weinberg questions, you can always do a Google search for Hardy-Weinberg AP Biology questions, or ask me for more questions. Have a good day. I'll see you again next time.